I want to thank the organizers of the meeting and both scientific and support and for inviting me to give this talk. So thanks very much. Today I'm going to talk about two moist static energy budgets. The first one is the first one is of the atmospheric boundary layer and the subcloud mix layer. I call them by two names, but I'll try and stick with subcloud mix layer because it's more specific. And then the second is the moist static energy budget of the troposphere, which you've heard about already, I think, from me and also certainly from Eric in his two talks. So first, some preliminaries on air-sea interaction. And you've probably heard this one, that the upper 2.5 meter, or any 2.5 meters of the ocean, but most usefully, the upper 2.5 meters of the ocean have the heat capacity equal to the whole heat capacity of the atmosphere. But that's the dry heat capacity of the atmosphere. We could also play games and say that the latent heat of the atmosphere, the amount of water that it tends to be evaporated in the atmosphere, is equal to about a 0.3 degree C anomaly over a 30-meter ocean mix layer. Oh, and that is, I calculated it and it kind of amazed me. This is like the sort of intraseasonal variability of sea surface temperature and heat content in the upper ocean that we see. So it's very possible, this doesn't prove anything, but it's very possible that the cycle of sea surface temperature can be coupled to the atmosphere in a meaningful way. So I said this already, that I will be talking about the subcloud mixed layer moist static energy budget and the tropospheric moist static energy budget. So first, the subcloud one, and I'm going to just show you a quick thing that I recently worked on where I did a mixing line analysis to separate out the sources of air and what sort of moist static energy they're fluxing into the subcloud boundary layer. And the subcloud boundary layer is important because it's the source for air that goes into the clouds. It's the subcloud mix layer. We've got surface fluxes, which are the only thing that are warming up and or consistently warming and moistening, consistently increasing the moist static energy by warming and moistening the subcloud mix layer. Evaporative downdrafts tend to be a little bit dry, actually, because they're coming from a saturation value at a colder temperature higher in the atmosphere, but they're not very dry. The real thing that distinguishes them is that they're cold, and they're quite cold, and we see them in the time series, those cold pools at the surface. And then we also have this subcloud mixed layer is a turbulent layer, so it's entraining air turbulently that has been in some sort of gross sense detrained from deep convection, maybe a long time ago, and has been descending and gradually cooling off by radiative cooling. So it's likely to be very dry because it's descended from a very cold temperature, and it's fairly, sort of dry and warm. So this one has a sort of ambiguous effect on the moist static energy budget, but it is mostly, before I say something wrong, I'll get to the result. So here we can actually use potential temperature we can use conserved variables to figure out what the sources of air are into the mix layer, because the surface flux, we actually know the surface fluxes from ship measurements, or for example, that's going to be the data set that I'm going to use to do this budget balancing. And for air that is just moving adiabatically, it should conserve its potential temperature. So here I've got an arrow including to represent dry entrainment. So it should be bringing this air that's just a bit warmer than the subcloud mixed layer. And I've drawn two lines. One is to represent times when cold pools were observed at the surface, and one is to represent times when they were not. So the red line is by far the most common, but the blue line is the average of the fairly common event, but much rarer compared to the background of the background conditions. And then if air is descending through a rain shaft, or a rain shaft is evaporating so that there's hydrometeors present and the air is descending, it will warm up as it descends, but it will, since there's liquid water present, it'll evaporate liquid water and it'll follow a wet bulb process. Equivalently, I could have used equivalent potential temperature, but wet bulb potential temperature has a nice property that when you evaporate water into it, you actually, if you come down to the reference pressure, the potential temperature and the temperature you observe will actually be the wet bulb temperature. So this is sort of an observable way of looking at it. And so the wet bulb potential temperature is actually remarkably uniform throughout the troposphere, especially once you get up here, which coincides with being above the shallow cumulus-humulus layer in the tropics. I haven't looked into that very much, but that's worth thinking about some more. And then it's also it's slightly cooling off as you go up here, but it turns out that if you use a model that it doesn't matter very much because it's changing very much. If you use a model that takes air from about a 2-kilometer layer and injects it in, you can calculate good mixtures of the boundary layer properties that are observed in the boundary layer. So, or mixed layer. So here I've done a sort of like, if you're an oceanographer, you'll recognize this as being like a TS diagram. In this case, this is potential temperature, which is close to the temperature we observe at the surface. And then instead of salinity, I have the specific humidity. Both of these things are conserved for the air. And the boundary layer air, the mixed layer air that I measure aboard a ship with a meteorological tower is these black dots here, and they all run together. So on top of the black dots, I just plotted a PDF of the dots. So most of the dots are here at this maximum. And then I've also plotted a dot for every time I make a measurement. I think this is 1 minute or 10 minute or 5 minutes. Sorry, it's lots of dots. It's fairly high frequency observations. So I've also put it for every black dot, there's also a dot of the downdraft potential temperature as it enters the boundary layer, and the surface potential temperature. The surface is warm and moist. The downdrafts are cold, and they lie both along this. I think it's dotted, but hard to see. This is a saturation specific humidity line that they actually are different pressures, but they nearly lie along the same line. And then the entrained air it is not along this line. It's in this very unsaturated, dry region, but it tends to be it's as warm as the surface, but as dry as the downdrafts. And so we can actually, for each, you can't see them, but for each realization, there's a triangle of surface properties, entrained air, downdraft air properties, and a boundary layer air property, which is a mixture of these three. And so we can actually figure out what fraction is responsible for each mixture. And I do this with the computer, but it's just basically so this is the mixture. So we have the two conserved variables, and we have fractions of each, and we multiply them up together to get the potential temperature and the humidity. The third line just says the sum of all the fractions equals 1. So we've got it all. And so we can eliminate that third line, and we just have to invert this, remit this matrix of the difference of this boundary layer and the source. I think this is right. I copied it out of my paper. The only work you have to do, and I do it, you can actually do it, you can do it algebraically because it's 2 by 2 matrix, and then I have like thousands of observations, and I hard coding and inverting a 2 by 2 matrix to thousands of observations, and then what you get is, so graphically, so here's one triangle of entrained air, downdraft air, surface air, and the mixed layer air is somewhere in the middle of those. So we can, that matrix is like a transformation matrix, and then we get, we can write new coordinates, which are, that matrix transforms it to new coordinates, which are downdraft fraction and surface fraction. And then 1 minus those two fractions is also the entrainment fraction. And so here it is in these coordinates, and it actually looks somewhat the same, but it pulls out some differences. And then from this, we can actually compute the moist static energy. If we have the fraction of each of these air end members, if you like, then you can compute the moist static energy, and we also know the properties of the end members. We can compute the moist static energy flux by each of the end members. Skip over that, and there's the, so here the moist static energy flux is due to the surface, the entrainment, and the downdrafts. And the surface, as I mentioned, is always warming and moistening. The downdrafts are always cooling. And I can tell you they're not moistening or drying very much systematically. The entrainment one is actually sort of interesting. The turbulent entrainment is interesting, but they're usually, they're warming and drying, and usually the drying is greater than the warming, so their moist static energy sink, but occasionally the warming is greater than the drying. So I haven't investigated why this is, but these ones are actually not so separated from the zero line as the surface and the downdraft counterparts. Okay, so I told you about the subcloud mixed layer moist static energy budget. And so we have downdrafts and entrainment flux is both balancing the surface flux warming or increase of moist static energy. Next, I'm going to talk about the tropospheric moist static energy. And there's a couple that we've talked about, some different mechanisms by which the ocean heat content and sea surface temperature affect synoptic and intraseasonal convection. And I mean, here we've talked a lot about intraseasonal convection. And we've talked a bit about both of these mechanisms already. So, but I'll sort of address these two in my own way now. So it could be that the surface moist static energy flux from the surface fluxes increases the moist static energy in such a way that reinforces intraseasonal oscillations and reinforces convection due to wind and sea surface temperature alignment. Or Eric introduced this in yesterday's talk, that balanced moisture convergence due to balanced hydrostatic circulations of a warm sea surface temperature can increase the moist static energy. And I don't know, I'll go on. So one other note to note is that note about the troposphere is in this near quasi-equilibrium, and Eric noted yesterday that the moisture is the important quantity that varies, and this is because the tropical atmosphere is near the equator. The planetary rotation is small, so the temperature profile is easily smooth. You can't support strong gradients in the temperature profile with balanced geostrophic circulations, as you could in mid-latitudes or polar latitudes. And so the temperature gradients are weak, and temperature profile is near a radiative convective equilibrium, and that's this weak temperature differences are just schematically represented on the right by flat isotherm horizontal lines. But moisture, on the other hand, if you have convergence near the surface, the moisture is represented by this green stuff, that green color here, and the moisture is, the temperature is much higher near the surface, so the moisture is also much higher. And if you have convergence, you can sort of imagine bulging this moisture up higher into the atmosphere and increasing the column amount of moist static energy. Another thing is you might think that the latent heating could warm the atmosphere up if we go back to the weak temperature, but it turns out the latent heating is very readily and quickly balanced directly by the adiabatic rising motion of the air. So it almost doesn't induce very much of a temperature anomaly. And then what temperature anomaly that it does induce quickly radiates away by gravity waves. It's like if you drop a rock into a pond, you don't expect that the place where the rock falls in and settles to have a lump at the top of the pond for very long, because the pond is a free surface and it rapidly radiates away that mass anomaly from dropping the rock in. I can just click it with this. So the column, for several reasons that I'm not going to go into it, and I think Eric knows better than me, but he didn't talk about it that much. The column moist static energy, this is a concept of quasi-equilibrium. The column moist static energy is linked to the circulation in the tropics. And the important part, because I've just argued for 5 minutes about why the temperature variant doesn't vary very much, Z doesn't vary at all at any given height. That GZ part is a constant. So the important thing that can vary in the moist static energy budget is the humidity, this green term, and the way that it can vary. Well, there's different ways it can vary, and I will look into 2 of those. And you've already seen, and I will say that the convergence of the moisture is central to the tropical circulations. And so we calculate, just a note on this convergence. We can take the advection and write it as a horizontal part and a vertical part. And it turns out that the vertical part of the vertical part of the advection can be, you can use the mass conservation to show that the vertical part of the advection can be written as a horizontal convergence, horizontal divergence. And when we integrate this term, it goes to 0, because if omega is not 0 at the top of the atmosphere, and it doesn't really have to be, but it kind of has to be if the pressure is 0. But also the humidity goes to 0 at the top of the atmosphere. And nobody should have a problem with omega, the vertical velocity, being 0 at the surface, because there's a rigid surface there. Then we get this horizontal advection term and this horizontal divergence term. And I've evaluated both of these terms, at least in the framework that I'm working with, although I think Eric has evaluated this from reanalysis. So in general, this advection term is not always small, I think. But in terms of the sea surface temperature gradient induced circulations, it is small. And the dominant term is this divergence term. So the question then becomes, so here's I'm going to just focus on the Mathur-Julian oscillation. So that's the austral summer cousin of the boreal summer intraseasonal oscillation, or sibling, I don't know, there's just 2 of them anyway. So, and this, I think you've seen some plots here, but in this plot, interestingly, the dashed lines, the purple dashed lines are the rain anomalies. And you can see underneath, which is why I put this one on the sea surface temperature anomalies. There's sea surface temperature anomalies, especially in the Indian Ocean. And well, in this, it doesn't resolve, the products they're using don't resolve it between the islands and landforms of the maritime continent very well. But you can also see some anomalies on the east side of the maritime continent. So the question is whether these a couple of tenths of a degree of sea surface temperature of the anomaly could feed back onto the Mathur-Julian oscillation by enhancing air-sea fluxes or inducing hydrostatic pressure gradients that drive frictional moisture convergence. So, and I'll just answer my question first of all. Turns out that the latent heat is the largest evaporation term by a factor of about 10. And the anomaly of latent heating is small, and it's out of phase with sea surface temperature because it's mostly driven by changes in the wind associated with the intraseasonal oscillation. Second, can it induce hydrostatic moisture convergence? Yes, it can be up to plus or minus 10 or 20 watts per meter squared, averaged over the central equatorial Indian Ocean, which is the place where you actually see it the most. So I wonder if that's related to the, I don't know why it's mostly there. There's problems with doing it over the maritime continent where there's lots of land. But anyway, you get a strong signal in the equatorial Indian Ocean. So, but first, let's look at the fluxes where the story is less clear. And to this, I'm going to use a relatively small number of events to illustrate this from dynamo. So first, this is the precipitation in accumulated precipitation over dynamo in the area, greenish, bluish area, and then the evaporation. And you can see that the evaporation is relatively steady, and that the precipitation falls in bursts. That shouldn't really surprise anybody. And also that the mean precipitation is about twice as big as the mean evaporation. So already we have a budget deficit of water that somehow we have to, the outgo is it's more than twice as much as the income locally. So there must be some, that means that there's some need for non-local moisture convergence or advection. And if we look at the individual events of precipitation observed during dynamo, these were 3 different legs, then the precipitation is a sink of water to the atmosphere, and it's shaded bluish purple down here. And there's also evaporation, which is just sort of a steady moistening along here. And then we had a microwave radiometer, which measured the amount of precipitable water over the ship. This was at 80 degrees east and on the equator. And the sum of all of those terms has to be 0, and we compute the moisture convergence over that location as a residual. And you can see every time it rains a lot, there's a demand for even more moisture convergence out of the budget. And the sign is maybe not particularly consistent at all times, but when we have a synoptic rain event that's embedded within an intraseasonal rain event, then you need synoptic moisture convergence in the atmosphere. Local just doesn't do it. And if we look at the phase of the sea surface temperature anomalies, here's outgoing long-wave radiation. So where it's low, it's cloudy, and I've repeated that with the black contours in each plot so you can orient yourself to that convective phase. The sea surface temperature actually warms up gradually after the convective phase and kind of stays relatively warm before the convective phase. And then right in the convective phase, it actually cools off very quickly. And then it kind of recovers gradually again. And this is, this may be considered a Hofmüller plot because it actually has longitude along the x-axis and time. Spot the Hofmüller plot. There's 1. There's 4. This is phase, but it's in some sort of phase. It's can be thought of as time, and but resolved according to the cycles of the MJO. And then the fluxes, interestingly, occur where the wind starts to be strong at the beginning of the convective phase, but the SST is still strong. They occur, the wind is probably actually also stronger at the beginning. So there's a strong heat flux here, and then there's drying. Is that the right sign? Well, it could be just wrong, or it's probably not. It's probably like what these fluxes are doing to the ocean. They're all so yeah, so I think the sign is right if you just negate it from what you were thinking. Well, there's two conventions. There's two sign conventions for surface fluxes. One is the negative of the other. So the only way it makes sense is that there's sensible heat fluxes here. And the latent heat flux, the cooling of the ocean, is occurring farther back in the intraseasonal oscillation. Well, what would happen, Charlotte Dumont has calculated this more rigorous. I mean, you can kind of eyeball it. You're trying to eyeball it from here, but Charlotte Dumont's actually calculated this, and what happens is the latent heat flux, which is the big moist static energy flux, is let's see, the solid line is with the SST varying, and then the dashed line is if you held the SST constant, more or less. So the latent heat flux is earlier, is stronger before this is the time of, I think it's the time of maximum rainfall. I looked this up and now I can't remember. Oh, it's actually the time of the maximum moist static energy in the atmosphere. I wrote it on here luckily because I didn't remember. And so this is just composited on intraseasonal time when the moist static energy is the highest. And so actually in either case, the latent heat flux is increasing the moist static energy when it's already large. It's not contributing very much to its increase. It's kind of smallish here. They're both positive, but kind of small. And including the changing SST makes the moist static energy flux a little bit larger before the event, and then it tails off quicker. It decays quicker during the wind and the moist static energy. This is when the wind increases later after the moist static energy. So that's why the latent heat flux is occurring there. And if you look at if you include the sea surface temperature, you can calculate this over all of the places where the MJO is, well, all of the tropics really, or all of the Indian and West Pacific Ocean. The sea surface temperature increases the moist static energy tendency by 1 or 2 watts per meter squared. So local increases due to changing the SST do something, and you can calculate it. But 1 to 2 watts per meter squared is, I think, kind of small and not sufficient to explain much. It certainly doesn't explain the hundreds of watts per meter square of condensation that we need to drive the precipitation. So the effect of this MJO sea surface temperature on the fluxes is small. Surface flux variability is driven mostly by wind, and the SST is not in phase with the wind. So it causes a sort of shifting of the surface fluxes rather than a real intraseasonal enhancement of them. And I also said that local evaporation is insufficient for column moisture anomalies, either in the mean or in storms. So they all require non-local moisture convergence. However, Eric once warned me that even small moist static energy sources might compensate moist static energy export by circulations and could destabilize moisture modes in the atmosphere. So this 1 to 2 watts per meter squared, it might not seem very large, but it might be helpful to, the atmosphere could, in theory, be quite sensitive to small destabilizations like that. So the second mechanism I'm going to talk about is the question is, does the sea surface temperature anomaly induce hydrostatic pressure whose gradient drives frictional moisture convergence? always have a lot of trouble describing this mechanism because of all the jargon that has to go into it. Sea surface temperature anomaly, inducing hydrostatic pressure anomalies, whose gradient, because drives frictional moisture convergence. Okay, so as a question, I managed to phrase it as efficiently as I could. So the flux anomalies are small, but suppose on intraseasonal timescales, the boundary layer is maintaining thermal equilibrium with the SST. It's quite different than the idea that the fluxes are changing. Well, maybe the fluxes are what is making this boundary layer in equilibrium with the sea surface temperature. But here we're not interested in the flux itself, which is changing it, but that the sea surface on intraseasonal timescales, the temperature anomaly in the boundary layer, I guess that's represented by this warm W here, is actually synchronous and in equilibrium with the warm anomaly that's at the surface. So that warm anomaly is going to drive a low pressure underneath it hydrostatically, and so that low pressure will induce convergence. So I'm going to compute the sea surface temperature induced wind divergence with the same model that Eric is suggesting. I think Eric suggested I use this model. There's an older model called Lindzen and Negum, which can be fixed up to do almost the same thing. I'm going to composite the trim microwave sea surface temperature on the real-time multivariate MJO index. This is the Wheeler and Hendon index that Eric was also showing. And I'm going to only composite it for November through April, so Southern Hemisphere summer, when the real-time multivariate index, its magnitude is greater than 1. And I'll filter the output of that spatial pattern with 100-day, 3.5-degree running means, and compute the induced pressure from the Back and Bretherton model from this sea surface temperature pattern. So here's the sea surface temperature pattern, filtered as I just described, for each of the phases of the real-time multivariate MJO index. And I put them, for some reason, for display purposes in this order, where the first, I think because you see in green contours, which you really can't see, but I'll highlight, you can see where the rain is strong. And then, so the red shading is where the sea surface temperature is high, and then the blue shading is where the sea surface temperature is low. And as I showed before, the sea surface temperature is high in advance of the rain anomaly, which is also attended by a wind anomaly, and then it's followed by a cold sea surface temperature anomaly. Let's see. The sea surface temperature actually is in red contours and the blue contours. Positive anomalies are red contours. The shading are moisture convergence. So red is moistening, can be confusing for some people, and blue is drying. So that's the result of this Back and Bretherton. What? Some meteorologists think that water is cold and wet. It should always be displayed in blue contours, and that red is a dry color. So it should. But I think that red is a positive, should always be used as a positive color, and there's really no right answer for this. So, okay. So now you, also hard to see. Now I've added these boxes here. This is my averaging region. You can see this one here, barely. So if I average over that box, you can see that in phase 8, there's actually really strong moisture convergence, strong moistening in the box. And in phase 5 and 6, there's strong drying in the box. If I average that moistening and drying in that box, the blue line shows the moisture convergence. And you can see that it's about plus or minus 10 or 20 watts per meter squared. And then the red line shows the sea surface temperature multiplied by 10. So it's actually multiplied by 100. It's actually plus or minus a tenth, or a little more than a tenth of a degree average. And so one of the problems with doing this you might get hungry to want to like calculate a sea surface temperature to ship during an experiment, but you can see that these depend on not purely on the Laplacian, but they depend on the second derivative of a noisy satellite. It's a composite, but it still ends up being a noisy satellite sea surface temperature field. And so this convergence is very wiggly, and those wiggles are they're hard to overcome observationally. So you actually have to composite a lot of events, and I even had to filter to make it look a bit more readable. You can see places where, well, actually here there's tropical instability waves, which are like 15 to 40 day oscillations in the north side of the sea surface temperature of the cold tongue in the Pacific, and so they alias pretty well into those sea surface temperature anomalies alias pretty well into intraseasonal stuff. So I wouldn't put too much, wouldn't read too much into that. So I assumed that it was, I think, 750 750 meters deep. I forgot. You make some assumption. I think I assumed that there was no pressure anomaly above 750 meters, which is about where the cloud base level is. And so, I think that's a pretty good assumption, because that level can go up and down to sort of compensate. In the free troposphere, it's a pretty good assumption that the temperature is fairly uniform throughout the free troposphere, and that's because of the action of the clouds and the gravity waves. So you have to sort of get below that, where the clouds aren't able to do this moist convective adjustment thing, and yeah, well, and I'm just throwing away all the other things all the other variability that is possible. Yes, but under that assumption, I throw them away, and I know that I'm just calculating the convergence due to the pressure, and just the pressure due to the sea surface temperature anomaly. Exactly. I think if you change, 10 minutes? An hour, maybe? What's that? The SST changing is the slow part. The atmosphere will respond to that really fast. No, I think I tailed it off to 0. I think that's what I did. So I was looking at that last night, and I can't remember right now, but I think I've done it both ways, and roughly, if you have it linearly decreasing to 0, then you'll get half as big a signal. Not quite the same, depending on your assumptions, you could make it be exactly half. Okay, so in this sea surface temperature induced convergence, I sent this result to Eric a year or 2 ago, and he said, oh, this is looking, I thought, oh, 10 to 20 watts per meter squared. It's not that big. It's certainly not enough to make up for, to explain the large anomalies we need in the rain. But Eric pointed out that that is about of the same order of magnitude as the advection that he's calculated from reanalysis with his colleague Kiran Maini and Maloney in 2011. So there's the moisture advection, and I've scaled the plots to have about the same magnitude, and so if you slide it on top, it's it's not quite in phase with any of the advection terms, but it's right in there in terms of doing the same amount of work as those advection terms. So this is the best I've synthesized this sea surface temperature convergence mechanism with the reanalysis. Although, Eric, I think you've done more with the BSISO now. All right, so the sea surface temperature-induced boundary layer moisture convergence explains a significant fraction of moisture advection, 20 watts per meter squared, or plus or minus 20 watts per meter squared average equatorial Indian Ocean moist static energy convergence. And, you know, this is blobby, so I said not to read too much into the bright blobs, but if we were to be really optimistic, it sometimes reaches 100 watts per meter squared, you know, averaged in some phases. And it's systematically 10 to 20 days ahead of, and by head of also, it's east of MJO convection in the Indian Ocean. And it's most observed in phases 7, 8, and 1. So I like to think of this as the Indian tropical atmosphere inhaling moisture, I guess, inhaling moisture before the convective phase of the MJO. All right, so that concludes that. And now I've thrown in some things which have popped up in this meeting, and I just have some plots that I can say some things about. So I guess I could ask for questions on the sea surface temperature convergence. I'll ask for questions. And I know you've seen that. You've seen this already, so you've got all your questions answered. Or not. Yeah, actually, we should actually look at observations of real pressure changes and real sea surface temperature changes to see if there's any, because that's so easy to do. I think it could be kind of noisy, but you've looked at it. What? I haven't actually looked at it for surface data. That's a good idea. One problem is that this was for, if you do it on the equator, your signal will be swamped by semi-diurnal cycles, which I guess you could filter out. That's just the way, there's a semi-diurnal tide in the atmospheric pressure, which has nothing to do with this. And as you get farther away from the equator, that's less important, but it's very big at the equator. Yeah, that's worth looking at. Or either BSISO or MJO, or just wherever you're at. I mean, it might be, at very least, it's a good way of telling us how deep to make our temperature anomaly. Because if on average a certain SST, there'll be a coefficient of pressure to SST, so that would be fairly useful. All right, so the next thing I'm going to throw in here is the response to a smaller scale sea surface temperature variation. And so this is a model, this is a paper that Eric Skillingstad is writing, and actually just got got accepted and by Eric, in this modeling paper by Eric Skillingstad. So we have this warm, 3-degree warm sea surface temperature patch, and then we blow wind across it and let a cloud resolving model generate convection over the patch. And you can see, depending on the wind, but in this case it's a 3 meter per second wind, that the convection is first triggered by the warmer sea surface temperature, but the clouds organize themselves and then they propagate away from the patch. So here's I think 5 days from the start of the simulation. Actually, maybe we should consider it like 3 days after the spin up of the simulation. The clouds are stronger, not in the patch, but a bit away from the patch. So they're propagating away. And interestingly, depending on the mean wind, you can sort of arrest, you can imagine these this convection ring is sort of a gravity wave-like response so the convection is pushing itself out ahead of itself continually, somewhat like a moist gravity wave. And you can, depending on the wind, you can arrest these gravity waves either over the sea surface temperature patch, or the gravity wave could push ever so slightly upstream, upwind, and such as this case. Here's this green shading is the rain, and here's this is the gravity speed in the negative, the upstream propagating gravity speed, and then with the mean wind added to it, and then the downstream propagating wave with the current, the mean wind added to it. It's just initialized, and it slows down and generates shear in the boundary layer. Just initialized with a constant wind, and at all heights. And then as it spins up, it generates a shear in the boundary layer. So, I'm not telling, this is a 6 meter per second wind case. This one is a 3 meter per second wind case, but that would be, the wind in the troposphere doesn't change very fast. In the free troposphere, it does change in the boundary layer, so that you can also assume there's some shear in there. But that shear is probably not very important for I think it's not very important for the propagation, because the convection is occurring above that level. Okay, so in summary, surface flux, entrainment, and convective downdrafts maintain the subcloud boundary layer near equilibrium, and local evaporation is a factor of 2, too small to balance precipitation in the mean, and storms require even more moisture, 5 to 10 times as much moisture as the evaporation. Circulations in balance with the hydrostatic sea surface temperature-induced pressure gradients can induce significant moisture and moist static energy convergence. I mean, not huge, but significant before intraseasonal convection. And we have to pay attention, since there's been some where people are getting excited about the idea of this sea surface temperature convergence mechanism. The wind and convective organization, I think that the wind is not constant, and convective organization is certainly not constant, but those things, there's some complexity in how those select the scales of interaction. So if we have very large 1,000 by 1,000 kilometer patch, probably at that point we have enough room to have several mesoscale systems and a synoptic scale thing going on, that maybe that these convective organization issues don't matter over a big enough scale, but over small enough scales, they do start to matter. Okay, and then that's my conclusion, but then this is the thing that, so if we just have I wrote the mixed layer depth H, and I put it in the denominator of this, I don't know, heating rate coupling parameter. I just called it lambda. It's basically the inverse of the mixed layer depth times rho Cp. So the temperature of the ocean mixed layer is equal to Q over the mixed layer depth, right? So if we take a spatial average of this, such as a scale resolved by a satellite or a model or some practical scale that can easily be resolved, and we want to get things right on in our any kind of model, a satellite or a conceptual model or a numerical model. So the spatial average is indicated by brackets. So if there's actually variations in the mixed layer depth and the heat fluxes that are not resolved by this mean scale of this average, but they're actually going on, and if we're interested in doing a process experiment where we actually measure these mixed layer depth and heat flux anomalies in the process experiment, we want to know if they're important. And if they're important on these scales, then they have a covariance which rectifies onto these scales. So we can get an effective mixed layer depth or inverse mixed layer depth We can flip it around eventually if we like, which is the average of the temperature variations of the mean heat flux, which is equal to the average mixed layer, inverse mixed layer depth plus this covariance of the average heat flux. Let's see if that's the interesting way of doing it or the useful way. There's some questions whether this is the interesting or useful way of doing it, or we should do it some other way. So we can play games with that. This is meant to be for discussion, I guess. I'm sure it's for discussion.